In this video, I'm going to be explaining how we can use this technique called substitution to find an indefinite integral. So in our last lesson, we used the power rule to find an indefinite integral. That's the rule that we always try and use. That's the most basic integration rule and the rule that we will use the most. However, sometimes we will also see other types of functions where we have to try and rewrite it so that we can use that power rule. And composite functions, or functions times another function, or functions divided by another function, may use this substitution process because we don't have a chain rule for integration. We don't have a quotient or a product rule. We're always trying to use this power rule. So the substitution allows us to do that. So in this first example, we have a composite function. We have an inside function, 2x minus 1, and we have an outer function, that radical or that square root. So because I can't just use my power rule on a chain, I need to use this substitution. So if I'm dealing with a composite function, generally I can substitute or use my u for that inside function or that inner function. So I'm going to say that 2x minus 1 is u instead. So if I substitute that in, now I take the square root of u, or I rewrite that using an exponent or a power, so u to the 1/2, and now I can use my power rule. But before we do that, we got some other steps that we need to go through. Because I can't integrate with respect to u, or integrate a function in terms of u with respect to x. We always got to make sure that what we are integrating in terms of matches the variable that we are deriving with respect to. So I got to somehow replace that dx with a du, and here's how we do it. We set u equal to that inside function, 2x minus 1, and then we can find the derivative of both sides. I know I want du, so let's find du. So if I derive both sides with respect to x, the derivative of u with respect to x is du dx, and the derivative of 2x minus 1 with respect to x is just 2. Well, I still don't have dx, but I could solve for it. So if I multiply both sides by dx and then divide by 2, now I have dx in terms of du. So I can go back over here and substitute dx with this quantity, du divided by 2. And now I can integrate my function in terms of u with respect to u. Before I do that, I'm going to get rid of my constants and move them out to the front. We don't need to integrate those. So du divided by 2 is the same as 1/2 du, so I'm going to take that 1/2 out to the front. So now I'm integrating u to the 1/2 with respect to u, and we can use our power rule and move forward. So if I add 1 to my exponent and divide by that new exponent, I get this quantity. Dividing by a fraction is the same as multiplying by its reciprocal. So if I take 1/2 and multiply by 2/3, I just get 1/3. And anytime we integrate, we always got to add that constant of integration. Don't forget about that step. So we have 1/3 times u to the 3/2 power plus our constant of integration. The last step we need to do is just replace what we substituted u in before with its original function. And so instead of u, I'm going to rewrite 2x minus 1, and we have our final indefinite integral. You can always check your work by deriving an indefinite integral and see if you get back to the original function that you started with. So remember that deriving and integrating work forwards and backwards, they cancel each other out. So if I derive my integral here, and then I should be able to get back to that original function. In order to derive this, I got to use the chain rule. So I'm going to take my exponent, multiply it in the front, subtract 1 from my exponent, and then multiply it by the derivative of the inside. And when I do that and simplify, I do in fact end up with that original function that I started with. So I can verify that I integrated correctly. Let's do another one. Again, we're dealing with a composite function. We have an inside function raised to a power. So the inside function is 3x minus 1. The outside function is that raised to the 4th power. And then we got a little constant out here that we don't need to worry about when we integrate. So the first thing we're going to do is set that inside function equal to u. We could then substitute it and rewrite our function. Remember, before we integrate, a function in terms of u, we got to make sure that we're doing it with respect to u. So now we got to substitute dx with du, or something in terms of du. So let's go back over here and integrate both sides, or I'm sorry, derive both sides. So the derivative of u with respect to x is du dx. The derivative of 3x minus 1 is just 3. Let's take a look at what we want to substitute. So sometimes we can substitute more than one thing. Sometimes we can substitute more than just dx. So I have this 3. If I just move it to the backside, because it doesn't matter what order we multiply things in, I can visualize it a little better. I have 3 dx. Well, I can actually solve this for 3 dx. So if I multiply both sides by dx, then du is equal to 3 dx. So I can actually substitute 3 and dx for du. And that helps and simplifies everything. Although it is possible, you could have used that 3 and put it out to the outside. You could have solved this for dx and substituted. It just would have required more steps in your simplifying process. But it's still possible to do it that way if you didn't recognize it. So now I want to integrate u to the 4th with respect to u. Everything's good to go. I can use my power rule, add 1 to the exponent and divide by the new exponent, and then add that constant of integration. I could rewrite it. So rather than dividing by 5, I could say I'm multiplying by 1/5. And then I could substitute back in my original function instead of u, and we can call it good. You could then derive this to check your answer and make sure you get back to the original function that you were dealing with. Let's get a little bit fancier here, involving a trig function. But we still have a composite function. We still have an inside function and an outside function, and we might also have a product rule, but let's see what happens. So if I take that inside function and I substitute it for u, and then I derive both sides of this, we can actually start to take a shortcut. Rather than saying du over dx and then multiplying both sides by dx, we can actually just say this is du on this side. And on the right side, we could take the derivative and just attach dx to the other side and just skip that multiplying both sides by dx. But make sure you are comfortable skipping steps before you just start doing it. Make sure you know why you're doing it. So now we got du equals 4x cubed dx. Let's go back to this original. I actually have x cubed dx. So if I just solve for x cubed dx, I could substitute both of those things. So let's solve for x cubed dx here and just divide both sides by 4. So now I have 1/4 du, or du divided by 4 is the same as x cubed dx. And now I can just substitute x cubed and dx for du over 4. That du over 4 is the same as 1/4 du, so I can take that 1/4 out to the front and integrate the rest of my function. So cosine of u with respect to u, I could then use my trig identities for integration. The integral of cosine is sine, so sine of u, add that constant of integration, and then substitute back in our original u. You could then derive this and check your answer, and it works. We should get back to the beginning. One more example. This is a bit of a challenge. This is a little bit more advanced than what my class is going to be doing, but this is just to show you that regardless of how crazy the function is, we could use u substitution. And there are actually other techniques when things get this complicated, but let's just do a little challenge here. So again, I got this composite function. I can set u equal to my inside function, 1 plus x squared. I could derive both sides, so du equals 2x dx. Again, skipping that step of just multiplying both sides by dx. Go back to my original function. When I substitute u, now I have x to the 5th, u to the 1/2. So not quite what I have over here. I can substitute an x dx. So if I just change x to the 5th to x to the 4th times x, then I can actually substitute x in dx. So solving for x dx, I just divide both sides by 2. And now I can substitute x dx for du over 2. But I still have this x to the 4th. I need to get it in terms of u. So I'm running out of time in this video, so I'm going to save the rest of it for the next video.